today we will be talking about torque, or also known as moment. Got a worksheet for you with the content you need, the theory you need to understand torque and moments, and also all the questions when they've asked on torque since 2015 on this worksheet. Got all the questions there, past exam questions, extracted and organized for you, and all my written answers. And both of those will be in the link in the description, so download that. All right, so what is torque? Torque is basically the rotational equivalent of linear force. It's a sort of turning force. It's referred to as the moment of a force. So how do we calculate this? Well, moment is just force times distance, but this distance is a perpendicular distance from the pivot to, and it's perpendicular to the line of action of the force. So the force and the distance have to be perpendicular to each other, which is important, and that will give you your moment, which is in Newton meters. A simple example, so this is the pivot point here, and it's 10, you've got to wait 10 meters away from it, and it weighs 10 newtons. And so the moment would be sort of rotational force would be 100 Newton meters, 10 times 10. But that's because the force and the distance are acting perpendicular to one another. If the force is acting at some angle, we'd have to find the vertical or the perpendicular component of that force, and then times that by 10. We'll see that when we do an example. And finally, you just need to know the principle of moments. That just says that for a body in equilibrium, the total clockwise moment equals the total anti-clockwise moment. So the sum of all the moments, trying to get it to move, forcing it clockwise is equal to all the moments forcing it anti-clockwise, and hence it's at equilibrium. That's all the theory you need to know, but this is really the fundamental equation here. But let's do some exam questions. Okay, so we've got a couple of questions here. Just run through these to consolidate that theory. Okay, so state the principle of moments. Well, so just stated, this is, for a body in equilibrium, the total clockwise moments equals the total anti, whoa, easy boy, anti-clockwise, pretty anti my writing style, moments. Jeez, we're getting lazy with it, huh? Okay, so for a lot of these, they'll give you some scenario, and on face value, it looks kind of complicated, but it's not. If you just take the forces and distances, pretty simple. So they give you this example here. So we've got some wheels hanging from some rod and also attached to some cord. That's basically what they're doing. They're explaining that. And you've got the weight of the rod as well, acting from the center of gravity, which is the middle. So by taking the moments about the end A, so we always have to pick a pivot point to take the moments about, because dependent on our pivot point, we're dependent on, the distance, how far away these forces are, and how large or small the moment is. Torque. So show that the weight of the wheels are 14 newtons. So because this is at equilibrium, the clockwise, total clockwise, and total anti-clockwise moments will equal each other. So for the anti-clockwise, we have, a force here from the cord, 22 newtons, and you notice that in this scenario, all of the forces are perpendicular to the distances, the displacements here from our pivot point. So that's good. We don't need to find any component. In the next one we will. Okay, so for this anti-clockwise, we have force of 22 multiplied by, this distance is, am I going to use a calculator? Yeah, feeling lazy. So the distance from the wall or A to this, where this force acts from, is 0.45 plus 1.4 plus 0.75. And I plugged that in wrong. 0.45 plus 1.4 plus 0.75. So 2.6. So the anti-clockwise moment is this, and that's going to equal to the clockwise moment. In the clockwise moment, we have weight, or the center of the weight of the rod, which is 19, multiplied by, well, this action in the middle. It's the center of gravity of the rod. So that'd be half of 2.6, which is 1.3. And then plus, well, the weight of this wheel, W, multiplied by distance away is 0.45, plus the weight of this wheel, which would be 1.4 plus 0.45. I won't use a calculator for that one. It will be 1.85. Okay, so that's all the clockwise moments. And so then we can just simplify for W. So we're going to get, well, 1.85 plus 0.45, 2.3. 2.3 W equals 2, 19 times 1.3, and then 22 times 2.6 minus that, 32.5. 32.5. So therefore W equals 2, this divided by 2.3. So 14.1. 14.1, which rounded to 2 significant 14 newtons, which is what they wanted. Cool, so that's just calculating clockwise and anti-clockwise moments, setting them equal to each other because it's at equilibrium. Determine the magnitude and direction of the force acting on the rod at the end A. Well, at this point, the wall will be friction between the rod and the ball will have some force which is forcing it back up, right? Back up, because otherwise this thing would just fall down. But it's being kept in equilibrium. And so it wants us to find what that force is. Well, as all of the forces are acting in the vertical direction or the y direction, we can just sum these up, find the magnitude of that force. So the sum of all these forces in the y direction, we have 22 acting up, minus 19 acting down, minus 14 and 14, so 2 times 14, both the wheels. It'll be what? 22 minus 19 minus 2 times 14. It's minus 25. So the magnitude will be 25 newtons. So we have a 25 Newton force, but it will be acting upwards, right? Because that's going to be due to Newton's second law. This thing wants to fall down, but the friction between the wall is pushing a force equal and opposite to that, pushing it up to keep it at equilibrium. So it would be 25 newtons up or upwards. Cool. Let's do this other one. And so with this one, okay, so again, it looks quite complicated, but I guess you can read through all this if you'd like. I'll go a bit quicker. This is the weight force here. It's 96 newtons. But this, in this case, it's not acting perpendicular to the lengths or the distances. So we're going to have to find the component of this, the sort of the perpendicular component of this. Before I even start, I can see that. To show the component of the weight, show that the component of the weight perpendicular to the plank is 59 newtons. So it wants us to find this perpendicular component, this component here of the weight. You can split this up into a triangle. So this is 96 newtons. This is 38 degrees, and you have to do this all the time within these torque questions. So we'll call this, let's call this, I don't know, just call it y. So this component, this y of this weight, will just simply be, well, sine 38 degrees. So I'm just splitting up, this is just vectors as opposite over 96. Okay, so y will equal to this wy, let's call it y component of the weight will equal to 96 sine of 38 degrees. Right, that's that. Because this thing is made up of x and y component, right? So by finding this, we're finding this. That's going to be useful in calculating in the moments. Sine 38 is 59.1, or rounded will be 59 newtons. Also, we showed that. So by taking the moments about, again, this picking the pivot point is A, with the plane calculate the tension. Okay, well now we have the vertical component or the perpendicular component, which is 59 newtons. So about this point, well, again, it's at equilibrium, right? It's not beginning to rotate. So we have, this in the clockwise, and these tension, and this 59 newtons in the anti-clockwise. So we get 45 times this length here from A to that 45 newtons, which is 1.5. Don't judge me. Plus 1.1, so 2.9 meters is the length of the rod, and that is going to equal to, well, the moment's acting the opposite direction, or in this case the anti-clockwise direction. So we have this tension times 1.5 and plus 0.3, so T times 1.8, T times 1.8, and then plus also 1.5, not times 96, because that's not the perpendicular to the distance. You need this 59, which we calculated before. So this would be 59 times 1.5. Right? It's important that we use that. Right? And so those equal each other because they're at equilibrium. So therefore we get 1.8 T equals 2. 45 times 2.9 minus 59 times 1.5, 42. 42, so therefore T equals 2, 42 divided by 1.8. So 23.3 newtons, so rounded to be 23. Cool. So there's two examples. Doesn't really get much harder than that, and you'll see in the worksheet. It doesn't really get any harder than that. The important thing is to always remember that you should calculate the force which is perpendicular to that distance. So there's plenty of examples here from the last 8 years on this worksheet, and I've answered them all for you. It doesn't really get much more difficult than the ones I just did there. Cool, that's it. Now I'm going to talk a little bit about balance and equilibrium. Okay, so I'm going to talk a little bit about balance and equilibrium because it's something that pops up all the time in physics, justifiably so, because for some reason, some peculiar reason, the universe always tends towards balanced states. The universe, if we take a holistic or large perspective on it, in all sort of systems and scenarios, it tends towards balance and equilibrium. So the universe has a sort of divine balance. Its essence is balanced. It just tends towards balanced equilibrium states, which is amazing because without that sort of property, inherent property that it has, I mean, I wouldn't even be here, you wouldn't even be here, we wouldn't be here. It takes a lot of balance to even produce intelligent life. Well, that's what it seems like. And so, when we look at this, it's very interesting that the universe does this. And the more you look at it, the more you observe the universe, the more you realize how balanced it really is. It's crazy. It's beautiful. It's amazing. And so a big component of my work is trying to get us, all of us, as we're learning, especially physics, to live in accordance with nature and emulate that. So one of the things I want you to ask yourself is, how can I be more balanced? It's a great question to ask yourself because the universe is so balanced and tends towards balance and seems to value balanced states. So how do we as individuals and being a part of, if not nature itself, be more balanced? Because it seems like the most balanced individuals are the people that we really want influencing humanity. So you should really ask yourself, how do I be more balanced in my life? How do I bring more balance to the world? Because from that place, we can definitely see that we thrive in balanced state. When we're out of balance, especially just on an individual level, we're really we're in a sort of chaotic, crazy state. It's not very good for us and people around us. Little take on balance, but the universe is divinely balanced and it's beautiful. That's it. If you need any A2 content, it is on my Patreon. Peace and love.